Have you ever wondered why almost every planet we see in the universe is round? Why gravity always seems to sculpt matter into perfect spheres, as if shape itself were predetermined? Have you ever questioned why the universe expands at exactly the rate it does, not so fast that matter flies apart before stars can form, and not so slow that everything collapses back into nothing? Or why the moon appears almost exactly the same size as the sun in our sky, allowing for total eclipses that are not only beautiful, but strangely precise? When you start lining these facts up, something about them feels unsettling. Why do so many independent conditions land so cleanly in place? Why does reality look less like chaos and more like a system tuned just tightly enough to work? What if the universe only looks perfect because we happen to live in one of the very few versions where anyone can notice it at all? Look around. We breathe an atmosphere with just the right pressure, on a planet spinning at just the right speed, orbiting a star calm enough to burn steadily for billions of years. Is that design? Destiny? Or did we simply win a cosmic lottery that almost no one ever gets to play? In this video, we're going to rewind everything back to 1 second after the Big Bang, when the universe was still a blazing soup of particles and forces, just beginning to settle into place. From there, we'll follow the trail of a few strange numbers in physics, explore ideas like the multiverse and simulated realities, and confront the unsettling logic behind the Anthropic Principle, all in plain language. Because maybe the universe isn't perfect in the way we like to imagine. Maybe it's just barely good enough tuned, not for beauty or meaning, but for a fragile kind of life. To flicker on for a moment, look up at the sky, and ask a dangerous question. Why am I here at all? By the end, you won't just understand why physicists obsess over certain mysterious constants. You'll have to face a harder thought. If we rolled the dice of the universe again, would you still exist? If you've ever stared into the night sky and felt that something is either very wrong or very right about all of this, stay with me. This video is for that feeling. That feeling that something is either very wrong or very right about all of this is not new. What changed, over time, was not the sky itself, but the story we told about where we stand under it. For most of human history, the universe felt small enough to hold in a story. The land beneath your feet was a disk, or a mountain, or a great boat of earth, ringed by a cosmic ocean. Above it, a solid sky arched like a dome, holding back the waters of heaven. In old Mesopotamian imaginations, the world was encircled by seas and roofed over by a hard firmament, a kind of inverted bowl separating the human world from the divine. If you lived inside that story, you did not have to ask whether the universe was made for you. Of course it was. The whole structure existed as a stage. Flat ground for people, waters for fish, sky for gods, an underworld beneath as a destination for the dead. Everything had a place, and your place was near the center of the drama. Ancient Greek thinkers imagined crystalline spheres carrying the stars and planets, nested like layers of an onion around a central earth. Classical Chinese traditions pictured layered heavens, stacked above a square earth under a round sky, with the emperor as the axis linking cosmos and society. Different cultures drew different diagrams, but the basic geometry was similar. Us in the middle. Everything else arranged around us, as if the universe were a set built with human consciousness in mind. If you looked up at the stars from that viewpoint, fine-tuning was not a problem. The world did not seem miraculously suited to you. It was assumed to be yours by default. Rivers existed so you could drink. The sun existed so you could see. The moon followed you at night like a lantern that had learned to hover. Then the sky began, slowly, to disobey. In the late Middle Ages, astronomers had already started noticing that the planets did not move in perfectly neat circles around Earth. They looped and wandered. Their brightness and positions shifted in ways that did not fit comfortably inside the old crystal shells. The heavens, which had been sold as the realm of perfection, started to show smudges and cracks. In the middle of the 16th century, a quiet, mathematically inclined church canon in what is now Poland arranged a different picture. Nicolaus Copernicus suggested that perhaps Earth was not the still point that everything else circled. Perhaps the sun sat near the center, and Earth was just another planet, moving. He did not publish instantly. The idea was dangerous, not only theologically, but existentially. If Earth was not the center of the universe, then neither were you. When his book finally appeared, it was less like a loud proclamation and more like a quiet rearrangement of furniture in the dark. You woke up in the same room, but nothing was where you left it. The Copernican shift is often told as a story about astronomy, but it is also a story about self-esteem. Imagine living in a world where every ritual, every myth, every political hierarchy had been built on the assumption that your place was central, and then reading a set of equations that calmly stated, "Actually, no, you are not even the center of your own local neighborhood." Over the following centuries, that demotion continued. The sun turned out not to be a special, exalted light, but a fairly typical yellow star. The Milky Way, that hazy band across the sky, revealed itself as a vast, rotating disk of stars, within which our sun was just one among roughly 100 billion others. Drifting in an ordinary spiral arm, even that galaxy, which once felt like the entire universe, became just one island in a cosmic archipelago. The observable universe seems to contain perhaps trillions of galaxies, each with its own swarm of stars, its own possible planets, its own quiet corners where some other consciousness might be asking very similar questions. With every new telescope, every new wavelength, the frame widened, and our apparent importance shrank. Writers like Douglas Adams captured this with humor that does not quite hide the sting. He describes an unremarkable little yellow star in an unfashionable end of a spiral arm, orbited by an utterly insignificant blue-green planet, whose inhabitants are still impressed by trivial gadgets. It is a joke, but also a diagnosis. We built our sense of meaning on being near the center, and now the map clearly shows that we are not. From this long sequence of downgrades, science distilled a principle: do not assume you occupy a privileged place. The Copernican Principle, as it is now called, tells us to treat our location in space as typical rather than special. On large scales, the universe looks roughly the same in every direction. There is no central throne, no cosmic capital city. If you shuffle vantage points, the view stays statistically similar. That principle has been remarkably successful. It underlies modern cosmology. When we build models of how the universe expands, how matter clumps into galaxies, how cosmic microwave background patterns arise, we assume that we are not looking out from a unique spot. We are just a random observer on an average world, in an average part of space, at an average time. But if you follow that principle all the way, something odd happens. Because here you are, a fragile arrangement of atoms on a small rocky planet, orbiting a star that is calm enough and long-lived enough to allow billions of years of evolution. The planet sits in a narrow band around that star where surface water can stay liquid. It has an atmosphere that is thick enough to hold heat, but thin enough that you are not crushed. Rich enough in oxygen for complex metabolism, but not so rich that everything spontaneously burns. Zoom out further. The galaxy you inhabit formed in a region of the universe where the density of matter was just right, not so low that gravity never pulled gas into stars, not so high that everything collapsed into black holes and dense clusters. The cosmic expansion rate is tuned such that galaxies had time to form before dark energy began accelerating everything apart. And when physicists write down the equations governing all this, they do not just find abstract symbolic relationships, they also find a set of very specific numbers. Constants describing the strength of gravity, the charge of the electron, the masses of quarks, the amplitude of primordial fluctuations, Those numbers appear, in our universe, to sit in a range that permits stable atoms, complex chemistry, long-lived stars, and planets with surfaces where liquid water can exist. Here, the Copernican instinct and the lived experience collide. The principle says, "You are not special." The evidence seems to whisper, "The conditions around you are strangely specific." For a long time, the default explanation was invisible intention. If the world seems well suited to us, perhaps someone or something made it that way. A designer, a creator, a cosmic engineer turning knobs behind the scenes until the universe produced minds, just as a watchmaker tunes gears so that a watch can keep time. Modern physics does not disprove that story, but it does something subtler. It shows how much of what feels inevitable is actually contingent. The values of physical constants, the timing of cosmic events, the structure of galaxies and planetary systems, all appear as outcomes rather than necessities. We can write equations that describe how the universe behaves once those numbers are given. But we do not yet have a deeper theory that forces those numbers to be what they are. So we are left with an unsettling tableau. On the one hand, we have learned that Earth is not the center of anything. Our star is ordinary. Our galaxy is one among uncountable many. On the other hand, we live in a universe whose rules seem uncannily compatible with our existence. We are not geographically central, but we do find ourselves in a kind of conceptual sweet spot. This tension is the quiet hum underneath many public debates about fine-tuning. When people look at the narrowness of life-friendly conditions and say, "The universe was made for us," they are responding to a genuine pattern. If the knobs were turned a little differently, the story of stars and planets might have ended before it began. When other people reply, "We are not special, we are just an accident," they are holding on to the Copernican impulse not to place ourselves on a pedestal. Both instincts are understandable. Both, in their own way, are trying to protect us from a certain kind of vertigo. But there is a third option, quieter and more troubling, that sits between them. Perhaps we do not live in a universe that was made for us. Perhaps we live in a universe where beings like us can exist at all, and that simple condition already biases every observation we can make. Perhaps the cosmos does not need to be optimized for life. It only needs to be just barely compatible with it, for long enough that somewhere, in some corner, a self-aware pattern of matter can arise, look around, and start telling stories about how perfectly everything seems arranged. From that perspective, our demotion is incomplete. We are no longer at the center of space, but in the space of all possible ways reality could have been, we may still be sitting in a very unusual niche. And the real question may not be, why did the universe choose us, but something more inverted. What if the universe did not choose us at all? And only in a universe like this could there ever be a we to feel chosen. The feeling of being somehow chosen dissolves quickly once you start asking what, exactly, is doing the choosing. Before you can say the universe is suited to you, you have to answer a quieter question. What is this you that feels suited to anything at all? At the human scale, the answer feels solid. There is a body. You can touch its surface, feel its weight, watch it age. It has a name, a history, a set of memories that hold together as a narrative. When you look in a mirror, you do not see physics, you see a person. But that familiar outline is a compression. If you peel it back gently, layer by layer, the apparent simplicity starts to come apart. Take the body as a whole. You can list its parts in ordinary language. Heart, lungs, brain, muscles, skin. It sounds straightforward, almost mechanical, like the exploded diagram of a machine. The heart pumps, the lungs exchange gases, the brain thinks, the muscles move, the skin protects. It is the scale where everyday intuition still works. Now, drop down one level. Each organ is not a single thing, but a crowded community of cells. The heart is not a heart. It is a vast assembly of muscle cells, pacemaker cells, blood vessel cells, each following local rules of chemistry and electricity. The lungs are carpets of cells, woven into delicate membranes, trading oxygen and carbon dioxide with the air. The brain is an enormous tangle of neurons and supporting cells, each one humming with tiny electrical events that no individual cell understands as thought. If you could shrink yourself down to the size of a cell and walk around, the body would not look like a body at all. It would feel more like wandering through a dense, busy city whose citizens have never heard of the word human. Within each of those cellular buildings, something even stranger is happening. The inside of a cell is not empty. It is a thick, crowded liquid where countless molecules bump, twist, bind, and break apart again. Structures we give names to: mitochondria, ribosomes, nuclei, are really just regions where particular patterns of molecules are held together long enough to be useful. Mitochondria act like power plants, shuttling electrons through chains of reactions to squeeze energy out of nutrients. Ribosomes sit like tiny factories, reading strands of genetic instructions and assembling chains of amino acids into proteins. The nucleus holds the genome, but even that iconic double helix is not a static symbol. It is continuously unwinding, being copied, repaired, tagged, packed, and unpacked as the cell's needs change. Viewed in slow motion, a cell is closer to weather than to a machine. It is a storm of interactions that somehow maintains its overall pattern long enough to divide, specialize, and join with other storms to form tissues. Step down again, and the storm dissolves into molecules. At this level, the variety of life collapses into a surprisingly small toolkit. Proteins, built from a modest alphabet of amino acids. DNA and RNA, built from a handful of nucleotide bases. Lipids, whose long hydrocarbon tails naturally assemble into membranes. Sugars, which can be bent and linked into endless shapes. Everything you call biology is just elaborate choreography among these few classes of molecules. Enzymes lowering energy barriers. Receptors changing shape when a signal binds. Ion channels opening and closing like gates under the push of voltage and chemistry. Nothing about these interactions knows anything about organisms or meaning. They are simply following the constraints of quantum mechanics and electromagnetism. Even that richness, though, is built on simpler pieces. Molecules themselves are just configurations of atoms. Carbon, oxygen, hydrogen, nitrogen, phosphorus, sulfur. Add in a few metals here and there, and you can account for almost everything in your body. The difference between a neuron and a raindrop is not in the types of atoms involved, but in how they are arranged and how they interact over time. And the variety of atoms turns out to be limited. In nature, there is a finite set of elements, from the simplest, hydrogen, up through increasingly heavier nuclei. Some catalogues list a little more than 90 elements that occur on their own without human intervention, from hydrogen at the lightest end to uranium near the heavy end. Everything you see, stars and stones, trees and blood, glass and smoke, is just different ways of stacking and linking those elemental building blocks. At this point, it can feel as though you have hit bedrock. Atoms have names, symbols, little boxes in the periodic table. It is tempting to take them as fundamental, but if you press further, the solidity fades again. An atom is mostly empty space. At its center sits a tiny nucleus made of protons and neutrons. Around it swarms a cloud of electrons, whose positions and momenta cannot be pinned down with classical clarity. The shells and orbitals you see in textbook diagrams are not literal planetary paths, but statistical patterns, places where you are more or less likely to find an electron if you look. The nucleus, in turn, is not indivisible. Protons and neutrons are composites, each made of three even smaller constituents we call quarks, held together by a field we describe as the strong nuclear force. There are different flavors of quarks, but the ordinary matter around you is built mostly from just two of them, traditionally labeled up and down. Those two types, bound into triplets, give you protons and neutrons. Add in electrons, which belong to a different family of particles, and you have enough ingredients for all ordinary atoms. By the time you arrive here, the grand narrative of the universe is made for us is already under pressure. You started with a person and ended with a handful of particle types obeying impersonal rules. Somewhere along that path, the warmth of the human story gave way to the cold vocabulary of physics. To see how precarious all this really is, you have to look not only at the particles, but also at the forces that govern them. In our current picture, nature uses four fundamental interactions. The strong force binds quarks together into protons and neutrons, and holds those protons and neutrons together in atomic nuclei. Electromagnetism makes charged particles attract and repel, holds electrons in their probabilistic orbits around nuclei, and underlies all of chemistry and biology. The weak force allows certain particles to transform into others, enabling radioactive decay and processes inside stars. Gravity pulls masses toward one another and shapes the large-scale structure of the cosmos, from falling apples to galaxies and galaxy clusters. At human scales, gravity feels like the dominant actor. It is the force you are most aware of when you stand, walk, or drop something. But on the scales where atoms and nuclei live, gravity is negligible. There, the strong force and electromagnetism set the rules. The strong force determines which nuclei can exist and how stable they are. Electromagnetism governs how atoms bond, how molecules form, how nerves transmit signals. What makes this set of forces unsettling is how delicately they seem to be balanced against one another. If the strong force were significantly weaker, many nuclei would fall apart, the periodic table would shrink, and complex chemistry would be impossible. If it were much stronger, nuclear reactions inside stars would proceed so violently that stars might burn out too quickly for life to evolve on orbiting planets. If electromagnetism were markedly different in strength relative to the strong force, atoms might not have stable electron shells, and the patterns of chemical bonding that make carbon-based life possible could vanish. Even the masses and charges of the basic particles matter. If electrons were far heavier, their orbits around nuclei would be tighter and more energetic, destabilizing many molecules. If the mass difference between protons and neutrons were not what it is, hydrogen might be unstable, or neutrons might dominate, radically changing the first light elements the universe produced. Subtle shifts in these values ripple upward through the layers, from nuclear physics to chemistry to biology to consciousness. None of this, by itself, proves anything about purpose or design. It simply shows that when we talk about us, we are really talking about a highly contingent cascade of structures that only holds together under a particular menu of conditions. The body you identify with is just the topmost pattern in a deep stack. Quarks and electrons arranged into protons, neutrons, and atoms. Atoms arranged into molecules. Molecules into cells. Cells into tissues. Tissues into organs. Organs into a body that, for a short time, can say the word I. If you stop the analysis at the level of the mirror, it is easy to believe the universe is tailored to that I. The world appears to meet you where you are. The air has the right composition to breathe. The surface has the right firmness to walk on. The temperatures you encounter day to day sit in a range where your proteins remain folded and functional. But if you chase that comfort down through the layers, the story shifts. You begin to see that what you call being at home in the universe is, at its base, a matter of compatibility between your particular arrangement of matter and one particular set of microscopic rules. Change those rules slightly, and the body fails to assemble. The cells never form. The molecules never persist. The atoms never bond in the right ways. From that angle, the question, was the universe made for us, becomes harder to hold on to. It may be that we are not the reason for the constants, but their consequence. We might be less like the goal of the process and more like a fleeting pattern that appears when a narrow range of parameters happened, once, to line up. And yet, knowing this does not make the feeling of being me go away. You can understand that you are made of quarks and fields and still feel pain, love, fear, curiosity. The reduction in description does not erase the reality of experience. What it does do is undercut a certain kind of certainty. If the self that sees the universe as finely tuned is itself a temporary product of a few forces and particles playing together in just the right way, then the claim "the universe is perfect for me" starts to sound less like an objective fact and more like something a specific pattern of matter would naturally say about its own survival. You can stand in front of a mirror, look yourself in the eyes, and know that the image is built from uncountable microscopic events you will never feel directly. You are both the person and the swarm, both the narrative and the physics. The unsettling question that lingers is not just what you are made of, but what follows from that. If we reduce to a fragile stack of contingent structures, how much weight can we really put on any story in which the universe is secretly arranged around us? If the story about us is resting on a hidden scaffolding of numbers, then the next uncomfortable step is obvious. You have to go and look at those numbers. And once you see how arbitrary they appear, it becomes harder to believe that reality is anything like a stable, necessary structure that could not have been otherwise. Physicists have a gentle phrase for some of the most important quantities in their equations. They call them fundamental constants. They sound dignified and calm, like pillars holding up a temple. In practice, they behave more like coordinates on a map no one remembers drawing. Take almost any law of physics you have heard of. The formula for the energy in light, the gravitational pull between masses, the relationship between temperature and motion in a gas. The symbols are neat and general. They say, if this, then that. But to use them in the real world, you have to plug in specific numbers. How fast does light actually travel in vacuum? How strong is gravity? Not in principle, but in practice. How large is the charge of the electron, or the mass of a particular quark? The equations give you relationships. The universe itself gives you the values. This is already strange. You might hope that a truly deep theory of everything would tell you not only how things interact, but also why every constant must take the precise value it does. You might imagine a universe where you could derive every number from pure logic, where no room is left for contingency. That is not the universe we live in. Right now, the numbers that steer our reality are, in effect, measured fact. They are written into our theories because nature appears to use them, not because we can prove that no other values were possible. In the middle of the 20th century, as quantum electrodynamics was being built, Richard Feynman became fixated on one particular constant. It is a dimensionless quantity that measures the strength of the electromagnetic interaction between charged particles. In physics, it is known as the fine structure constant. In everyday language, you can think of it as the dial setting for how strongly light and matter talk to each other. If you combine several other constants in a specific way, the charge of the electron, Planck's constant, the speed of light, you get a pure number, a little smaller than 1 divided by 140. When physicists plug this number into their calculations, atomic spectra and scattering experiments come out right. When they try to change it, even in thought experiments, the structure of atoms and the chemistry that rests on them starts to warp and break. Feynman called it one of the greatest mysteries of physics. Why this number? Why this strength of coupling? Why not a little larger or smaller? He joked that every good theoretical physicist keeps the value written on the wall and worries about it in secret. The joke works because it touches something real. Here is a number that seems woven into the fabric of reality, yet our best theories treat it as a given, not as a consequence. And it is not alone. There is a constant that sets the strength of gravity in Newton's law, controlling how strongly masses attract each other. There is Planck's constant, which fixes the scale at which quantum effects become important and tells us how grainy action is at microscopic levels. There are parameters describing how different quark types mix, how the weak force operates, how the Higgs field gives mass to particles. There is a cosmological constant or dark energy density that determines how fast the expansion of the universe accelerates at late times. Each of these quantities shows up in different corners of physics, like recurring motifs in a piece of music. Change them, and the melody of the universe changes. But in our theories, they remain inputs. We look at the world, Ask it what numbers it is using, and then write those down so that our equations will match. This is not how many people picture science. The popular image is of a discipline that explains everything from first principles, where nothing is arbitrary. The reality, at least for now, is more modest. Physics has been extraordinarily successful at revealing patterns and constraints. It tells us what cannot happen, or what is overwhelmingly unlikely, given the current rules. But at the level of the constants, it mostly says, this is how things are, as far as we can measure. The history of those measurements is its own quiet epic. At the end of the 18th century, Henry Cavendish set up an experiment that now seems almost impossibly delicate. He suspended a horizontal rod from a thin wire with small lead spheres on each end. Nearby, he positioned larger lead spheres. Gravity pulls every mass toward every other mass, but the force between the spheres is unimaginably tiny compared to everyday pulls like the weight of an apple. Cavendish watched how the rod twisted, ever so slightly, under that faint attraction. And from that twist, he inferred the strength of gravity. From those tiny deflections in a laboratory, one could estimate the mass and density of Earth and write down a numerical value for the gravitational constant. A single number, extracted from faint motions in a wooden shed, became one of the knobs controlling our models of stars, galaxies, and cosmic evolution. Today, the tools look different, but the logic is the same. Atomic clocks compare the ticking of quantum transitions to measure time with incredible stability. Particle accelerators smash beams together to probe how particles scatter and decay, letting us reconstruct their masses and interactions. Laser interferometers watch the stretching of space-time itself when distant black holes collide. Across all of this technology, the goal is still to read the numbers that the universe is already using. The unsettling part comes when you ask what would happen if those numbers were not quite what they are. Imagine turning the gravitational constant up or down. If gravity were much weaker, gas in the early universe would find it harder to collapse into stars and galaxies. The expansion would carry matter away before it could form dense, long-lived structures. Stars might be rare, diffuse, or simply never ignite. If gravity were much stronger, any region of slightly higher density could collapse quickly, forming black holes or extremely massive stars that burn through their fuel rapidly and explode. In neither extreme does there seem to be much room for the kind of stable, sun-like stars that can warm planets for billions of years. Or think again about the fine structure constant. If the electromagnetic interaction was significantly weaker, electrons would be only loosely held by nuclei. Atoms might not have well-defined shells, and chemistry would be dull and fragile. If it were much stronger, electrons would hug nuclei too tightly. The sizes of atoms would shrink, and chemical bonds might form and break in radically different ways. In some ranges, complex molecules might be impossible altogether. Carbon chemistry, the kind that underlies life as we know it, seems to require the electromagnetic coupling to sit in a relatively narrow band. The masses of the basic particles matter just as much. The slight mass difference between protons and neutrons helps determine which nuclei are stable and which decays are allowed. If that difference were reversed, hydrogen could become unstable, or neutrons could fail to bind in the ways needed for the early universe to make the light elements that serve as raw material for stars. If the electron mass were much larger, the quantum structure of atoms would change in ways that ripple up through chemistry to biology. In each of these thought experiments, nothing magical happens. You are not invoking new forces or spirits. You are simply moving the slider on a few parameters and watching entire classes of structure appear or disappear. Stars or no stars, complex chemistry or none, stable nuclei or a universe of short-lived fragments. From the vantage point of a living being, it is hard not to feel something like vertigo at this. The constants that define our world seem to occupy a small, special-looking region in the space of all possible values. We do not know how large that space really is or how it is populated. We do not even know if it makes sense to talk about those constants varying freely at some deeper level. But within the toy models we can analyze, the pattern is clear. Life, as we understand it, requires certain combinations, and most combinations do not work. This is where the numbers begin to feel haunted. We can see that if they were different, we would not be here. We can, in some cases, estimate how sensitive various processes are to changes. What we cannot do is say why the universe bothered to land in the range where we are possible. Some physicists hope that a future theory will remove the mystery. Perhaps, in a deeper framework, there is no freedom at all. The constants might emerge from geometry or symmetry in such a way that they could never have been otherwise. In that case, the apparent fine-tuning would dissolve. The universe would simply be what it had to be, and life would either appear or not appear as a side effect. Others suspect that the arbitrariness is real, that there may be many possible consistent sets of constants, corresponding to different possible worlds, and that we simply inhabit one of the few that support observers. In that view, the constants we measure are like the local weather in one tiny region of a vastly larger space. They feel inevitable only because we have never experienced anything else. In both pictures, the numbers retain their unsettling character. Either they encode deep, hidden necessity that we do not yet understand, or they reflect a contingency we cannot yet explain. In both cases, our usual habits of thought, imagining that things are the way they are because they were meant to be, or because they could not have been otherwise, run into a wall. You can write the fine structure constant as a neat ratio, speak smoothly about the strength of gravity, memorize the values that your calculator uses. But beneath that familiarity, there remains a simple fact. The universe is using specific numbers, and we do not know why those numbers and not others sit at the foundation of our reality. If the self is a fragile stack of structures perched on top of those values, then the terror in these constants is not only mathematical, it is existential. Change a few of them, and the stack never forms. Keep them as they are, and a short-lived pocket of matter develops the capacity to notice how improbable it seems and to wonder whether there is any deeper story at all hidden behind the numbers that permit its questions. If the terror in the constants lies in how easily they could have been different, the terror in the early universe lies in how quickly they began to matter. By the time the cosmos had lived through its first human breath, most of the script was already written. For you, a second is nothing. You can blink, tap a key, say a short word. It feels like the smallest useful unit of experience, the grain at which your awareness updates. You notice time at the pace of heartbeats and syllables. For the universe, a second is an epoch. To even talk about the first instant, language has to stretch. In the unimaginably early phase after the Big Bang, there is no clear separation between space, time, and the fields that fill them. Physicists give that phase names like the Planck era, but the labels are more like signposts at the edge of a fog than precise addresses. In that regime, our usual equations break down. Curvature and quantum effects are so extreme that talking about particles or forces in the ordinary sense does not make much sense yet. What we do think happened, as the universe expanded and cooled out of that initial opacity, is a sequence of symmetry breakings. Very close to the beginning, it may have been that all the fundamental interactions we now separate into four were aspects of a single, unified force, described by a highly symmetric field. As the temperature dropped, that symmetry fractured. The strong interaction, which glues quarks together, peeled away first. Later, the electroweak force split into electromagnetism and the weak interaction. Each of these transitions changed what kinds of particles could exist, how they moved, how they combined. It is tempting to imagine these breakings as catastrophic shatterings, but you might think of them more like phases of matter. Water vapor condenses into liquid. Liquid freezes into ice. The underlying stuff is the same, but the pattern of organization changes, and with it, the rules of behavior. The early universe is passing through its own sequence of phase transitions. But instead of changing from liquid to solid, it is changing from one set of physical laws to another. Somewhere in this early history, there is also a phase we call inflation. According to this idea, a peculiar form of energy in the vacuum, drove an enormously rapid expansion of space itself. In an instant so brief that calling it a fraction of a second feels generous, the universe's size ballooned by an extraordinary factor. Tiny quantum fluctuations, random jitters in energy density, were stretched out from subatomic scales to cosmic ones. Later, those stretched ripples would seed the formation of galaxies and clusters. The faint mottling in the cosmic microwave background, the pattern of large-scale structure we map with telescopes, can be traced back to this period of frenetic swelling. Again, the detail is full of debate and open questions, but the broad picture is clear. The early universe was not a calm, uniform haze, slowly drifting outward. It was a storm of transformations, with each stage constraining what could come next. After inflation ended, the universe settled into a more sedate, but still furious, expansion. It was filled with an extremely hot, dense plasma of fundamental particles. Quarks and gluons tumbled in a kind of firestorm, constantly colliding and exchanging energy. Particles and their antiparticles flashed into existence from radiation and annihilated back again. As the temperature dropped, quarks became confined into protons and neutrons. This confinement is not a matter of choice. It is a feature of the strong interaction. Quarks cannot roam freely at low energies. They bind into triplets and stay that way. The familiar nucleons that later sit at the heart of every atom were forged in this phase transition. At around the same time, the electroweak symmetry broke. The single electroweak force differentiated into electromagnetism and the weak nuclear force. Massless fields in the early, symmetric state acquired mass through their interaction with the Higgs field, which took on a non-zero value everywhere in space. Particles that had previously been racing around at light-like speeds now moved more sluggishly. The menu of allowed reactions shifted. By the time the cosmic clock had ticked for roughly 1 second, a lot had happened. The temperature of the universe had fallen from incomprehensible heights to a still unimaginable, but more tractable, range of roughly 10 billion degrees above absolute zero. The particle zoo had thinned out. The most exotic species had largely annihilated or decayed away, leaving a simpler cast: photons, neutrinos, electrons and their antiparticles, and the newly formed protons and neutrons. Crucially, the relative abundance of protons and neutrons was now frozen in. At higher temperatures, the weak interaction kept converting one into the other, maintaining a kind of equilibrium. As the universe expanded and cooled, those interconversions became less frequent. Eventually, the rate of transformation dropped below the rate at which the universe was changing, and the ratio got stuck at a particular value: several protons for each neutron. That simple fraction, stamped into the fabric of matter when the universe was about a second old, would later dictate how much helium formed in the first few minutes, and how much hydrogen was left over. It is a small, almost bureaucratic detail, one process falling out of equilibrium with another. But from it follows the basic chemical inventory that stars will inherit. In that same first second, neutrinos, nearly massless, ghost-like particles that interact only very weakly decoupled from the rest of the plasma. After that point, they more or less streamed freely through the cosmos, carrying with them a fossil record of this early era. Their existence is a reminder that the universe is full of relics from times and conditions we can no longer directly access. Space itself, at that moment, was tiny compared to what you see now, but it already contained the blueprint of everything that would unfold. The region that would one day grow into the patch of universe we can observe today was then an inconceivably small volume filled with this roiling plasma, its properties already constrained by the values of the constants and the outcomes of the symmetry breakings. To describe this, it is easy to slip into inevitability language. You might say, once the universe passed through these transitions, once the ratios and couplings were set, everything else followed, step by step. Hydrogen and helium formed. Clouds collapsed. Stars ignited. Galaxies assembled. Planets condensed. Life emerged. You arrived. But inevitability is an interpretation laid on top of the physics, not something the equations themselves say. They tell you that if the universe starts with certain conditions and values, then particular patterns are overwhelmingly likely to form. They do not tell you why those starting points obtained, or whether they had to. That distinction matters. Imagine, for a moment, a different universe. Same basic framework, quantum fields, general relativity, some set of forces. But in this universe, the parameters are slightly shifted. Perhaps the mass difference between protons and neutrons is altered. In that case, the freeze-out ratio of protons to neutrons could change, or the existence of stable hydrogen could be compromised. Without stable hydrogen, Big Bang nucleosynthesis would leave a different mix of elements. Stars, if they formed at all, would have very different fuel, lifetimes, and behaviors. Or imagine that the pattern of fluctuations imprinted by whatever played the role of inflation had a different amplitude. If those primordial ripples were much smaller, gravity would struggle to amplify them into full-fledged galaxies. The universe would remain smooth, lacking the dense knots where stars and planets can assemble. If the ripples were much larger, matter would rush into gravitational wells so efficiently that huge black holes and extremely compact clusters would dominate, shredding delicate structures. The point is not to map out every hypothetical. It is to see that the actual universe, even at the age of 1 second, was already sitting in a narrow region of possibility space. It was expanding at a particular rate, cooling at a particular pace, filled with particles in particular proportions. Because the constants and initial conditions had taken specific values, if those values had been elsewhere, the first second would have led to very different downstream worlds. From your vantage point, billions of years later, it is hard to feel this contingency. The world seems stable. The constants seem eternal. Gravity feels like a simple, slow pull. The sun rises every morning. At human scales, the universe is reliable enough that you can build calendars, cities, and memories. But beneath that reliability sits a history that moved with terrifying speed. In less than the time it takes you to inhale and exhale once, the universe transitioned from a chaotic quantum froth to a hot, expanding plasma with a defined set of forces, particle types, and ratios. The parameters that make your chemistry possible were already, for practical purposes, fixed. This is one way the idea of fine-tuning becomes more unsettling. It is not just that the constants have to fall in certain ranges, it is that their consequences are enacted almost immediately. There is no long period of trial and error on cosmic scales. There is no laboratory of many universes where settings are adjusted until life appears. Whatever values reality uses, it commits to them from the start. And the first second is the moment that commitment begins to crystallize into the familiar physics you can write down on a blackboard. If you look at a human life, you can tell stories about formative moments. The first time someone spoke to you in a way that changed how you saw yourself. The decision to move or stay. A chance meeting that rearranged your path. But you also know that before any of that, there were events you did not choose. The particular DNA you inherited. The circumstances of your birth. The first second of the universe is something like that on a cosmic scale. It sets conditions you will later build entire narratives on, without ever having had any say in them. By the time matter in that newborn universe had experienced its first second, the future was not predetermined in detail. No specific star, no particular planet, no individual mind was written into the script. But the range of what could plausibly emerge had been sliced down enormously. From then on, the universe would largely be exploring the implications of what had already happened. Expansion, cooling, element formation, structure growth. All of it unfolding under rules that had already been narrowed. The dice were not only rolled, they were also already bouncing toward the table. When you sit here now and ask whether the universe is fine-tuned for you, you are asking a question that reaches back into that first second. Was there any freedom in how those transitions played out? In what values the constants took? In how the early fluctuations were arranged? Or was it all, somehow, necessary? Part of a deeper structure we have not yet glimpsed? We do not know. What we can say is that the universe did not wait long to become specific. It did not spend ages wandering through different rule sets. It chilled through a sequence of thresholds, and with each threshold, possibilities fell away. From a human perspective, that is both humbling and strangely intimate. The warmth in your hands, the structure of your cells, the chemistry of your brain, all lean on choices that seem to have been made when reality was barely a second old. If the universe ever locked in its fate, it did so while it was still too bright to see, too dense for light to travel far, too young for anything like an observer to exist. You arrived much later, but when you look back, you are staring at the aftermath of decisions that shaped everything you call normal. And somewhere in that realization is the quiet, unnerving thought: if those early conditions had been different, there would be no eyes to look back at all. If the universe began committing to its rules in that first bright heartbeat, then somewhere inside that rush of decisions sits a quieter one, almost invisible. Which of two nearly identical particles would be just slightly heavier? It sounds trivial, like a rounding error in the code of reality, until you realize how much of the later story depends on that tiny tilt. On paper, protons and neutrons look like siblings. They are both made from three quarks, bound by the strong interaction. Both feel all four fundamental forces. Both sit pressed together in the nuclei of atoms. At everyday scales, they are the anonymous bricks from which matter is built. Their differences seem modest. The proton carries a positive electric charge. The neutron does not. The neutron is very slightly more massive than the proton, by an amount that, compared to their total mass, is only on the order of 1 part in 1,000. In more human language, if you treat the proton as a reference, the neutron outweighs it by about 0.1%. That is the kind of discrepancy you would normally ignore. If you picked up 2 stones and one was heavier by that fraction, you would not feel the difference in your hand. Nothing in your intuition about weight or size is tuned to notice such a small gap. But the universe is relentless about energy. Systems prefer lower energy states, the way a rock prefers to roll downhill rather than hover halfway up a slope. When there is a way to rearrange things so that mass and energy decrease, the rearrangement tends to happen, unless something forbids it. For a free neutron, the path downhill is to become a proton. That small extra mass can be converted into motion and new particles. Through the weak interaction, a neutron can transform into a proton, releasing an electron and an antineutrino. The total bookkeeping of charge and energy and lepton numbers stays balanced, but the identity of one of the nucleons changes. This transformation does not happen instantly. A neutron floating alone in space is unstable, but not explosively so. On average, it takes around 1/4 of an hour for half of a collection of free neutrons to decay. That lifetime is long enough that neutrons can play an important role in the early universe, but short enough that, left to themselves, they do not survive indefinitely. Protons, by contrast, appear to be stable on timescales far longer than the age of the cosmos, at least as far as our experiments can tell. In the energy and interaction environment we inhabit, there is no easy downhill route for a proton to shed mass while conserving all the necessary quantities. So it endures. This asymmetry, neutrons decaying into protons, but not the other way around, is a direct consequence of that tiny mass difference. If the neutron were the lighter one, if the sign of the gap were reversed, the downhill path would run the other way. Protons would be the unstable species, and neutrons the survivors. Now, place this fact back into the furnace of the young universe. In the earliest instance, when temperatures were extremely high, protons and neutrons were interconverting rapidly. Collisions and weak interactions shuffled up and down between them. In that regime, the relative abundance of the two was governed by thermal equilibrium and their mass difference. Roughly speaking, heavier states are slightly disfavored because they cost more energy, so neutrons were already at a disadvantage. As the universe expanded and cooled, the rate of those interconversions dropped. The weak interactions that allowed protons to become neutrons and neutrons to become protons could no longer keep up with the cosmic clock. At a certain point, the ratio of neutrons to protons stopped tracking the falling temperature and froze out at a value of roughly 1 neutron for several protons. After that, the decay clock started to matter. Free neutrons that failed to be captured into nuclei began to transform into protons on that characteristic timescale of minutes. By the time the universe had expanded and cooled enough for the first stable nuclei to form in Big Bang nucleosynthesis, the neutron population had thinned further. Almost all of the remaining neutrons were quickly bound into helium, each helium nucleus containing 2 protons and 2 neutrons. The rest of the protons, more numerous, were left mostly as hydrogen nuclei. The overall outcome of this process is simple to state and profound in its consequences. The primordial universe emerged with a composition of roughly 3/4 hydrogen by mass and 1/4 helium, with only trace amounts of other light elements. This ratio sets the initial conditions for all later chemistry and astrophysics. Hydrogen, being just a single proton with an accompanying electron, is the fundamental fuel of ordinary stars. In the cores of stars like the Sun, hydrogen nuclei fuse through a series of reactions into helium, releasing energy that counteracts gravitational collapse and produces the light and heat that bathe surrounding planets. The long lifetimes of such stars, measured in billions of years, depend sensitively on there being plenty of hydrogen to burn and on the reaction rates set by the same constants we have been quietly following. Helium, while less directly useful for chemistry, plays a crucial role in stellar structure and evolution. The balance between hydrogen and helium shapes how stars ignite, how they age, how they die, and what heavier elements they ultimately forge. If you change the initial proton-neutron ratio, you change that balance. If neutrons had been more plentiful when nucleosynthesis began, more of the primordial material would have ended up in helium and other heavier nuclei. Hydrogen would be scarcer. Stars might ignite differently, burn faster, or not form at all in the familiar way. If neutrons had been rarer, perhaps because they decayed more quickly or because the mass difference was larger, hydrogen would dominate even more completely, with helium and other species reduced. That, too, would alter stellar behavior. But the most dramatic scenario is the one where the mass ordering flips. Suppose, in some alternative universe, that the neutron were very slightly lighter than the proton rather than heavier. In that world, the downhill direction of beta decay would run from proton to neutron. Free protons would be unstable. Given time, they would convert into neutrons plus other particles. In such a universe, isolated hydrogen would not be a stable ground state. You could not have an atom made of a single proton with a single electron orbiting it for long. The proton would eventually transform, leaving behind a neutron that cannot hold an electron in the same way. The simplest, most abundant element in our universe would be missing or fundamentally altered. Without stable hydrogen, the chain of cosmic events shifts radically. The early universe's nucleosynthesis would likely drive more of the available baryons into tightly bound configurations like helium or even heavier nuclei, depending on details. The calm sea of hydrogen that fills interstellar space in our universe would be replaced by something more inert. The familiar cycles of star formation, where hydrogen clouds collapse under gravity, heat up, and ignite fusion, might never operate. Even if some kind of stellar object formed, its fuel, structure, and lifespan would bear little resemblance to the stars that light our sky. Without long-lived, steadily burning stars, the window of time for complex chemistry on surrounding worlds narrows or disappears. Planets, if they existed, would orbit a different kind of furnace, or none at all. And at a more intimate level, the chemistry you rely on is built in part on hydrogen's ability to form bonds, particularly with carbon, oxygen, and nitrogen. Water is hydrogen linked to oxygen. Hydrocarbons are chains of carbon and hydrogen. Proteins, nucleic acids, sugars all incorporate hydrogen as an essential partner. Remove stable hydrogen from the menu, and you do not just lose stars, you lose the specific, flexible chemistry that underlies known life. All of this flows from a mass difference so small that, on a relative scale, it looks like a footnote. A fraction of a percent determines whether neutrons or protons are the default survivors, whether hydrogen persists or is eaten away, whether the early universe's element mix favors long-lived stars or something utterly foreign. Physically, that mass difference arises from the interplay of the strong interaction, which binds quarks together, and electromagnetism, which makes charged configurations slightly more or less energetic. The neutron contains a different arrangement of up and down quarks than the proton, and the way those quarks move in the quantum sea inside each nucleon leads to a slightly different effective mass. That story can be told in equations and lattice simulations, but underneath it, the same question returns. Why this exact balance? Why this precise outcome and not another? From a human perspective, it is tempting to reinterpret this as intention. The mass difference looks like a careful choice. Make it much larger or much smaller, and the universe as we know it dissolves. But from inside physics, what you have is simply a parameter that seems to have landed in a narrow range, whose deeper origin is still opaque. This is what it means for a number to feel haunted. You can trace its consequences through cosmic history, from the first second to the hydrogen in your glass of water. You can calculate how different things would look if it were nudged one way or another. You can show that your very existence, as a pattern of atoms held together for a short while, depends on it being what it is. What you cannot do, yet, is say with any confidence that it had to be that way. So when you hear that the neutron is only very slightly heavier than the proton, it sounds like trivia. It is the kind of fact that lives on the margin of a textbook page, but if you pull on it, quietly, you find that an entire universe, one with hydrogen, stars, water, and minds, is hanging from that slender thread. If an entire universe can hang from a tiny mass difference between two particles, the next question is uncomfortable in a different way. How do we know any of this is real, and not just a story our equations tell each other on a chalkboard? At some point, you have to look up from the math and ask the sky to answer. One of the clearest answers arrived in a moment of darkness. In the late 19th century, during a total solar eclipse in the town of Guntur in India, an astronomer named Pierre Janssen set up a new kind of instrument to watch the sun disappear. He was not interested in the familiar disk of daylight or the drama of the moon sliding in front of it. He wanted to see the thin, ghostly atmosphere around the sun, the corona, and in particular, the colors of light it emitted. Those colors are not just pretty. When you pass light through a spectroscope, it spreads into a spectrum crossed by bright and dark lines. Each element leaves a unique pattern of these lines, like a barcode. By reading the pattern, you can tell which atoms are present, even if they are unimaginably far away. During that eclipse in the year 1868, Janssen saw something strange. Among the known lines, there was one bright yellow line that did not match any element measured on Earth at the time. Independently, an English astronomer, Norman Lockyer, saw the same line and argued that it must come from a new element in the sun, unknown in any earthly laboratory. They named it helium, after the Greek word for the Sunday. It would take decades before helium was isolated on Earth, in mineral samples and later in natural gas. But in that first moment, a new ingredient of the universe was discovered not by digging into rocks, but by watching starlight go dark. The sky revealed that it contained something our planet had not yet shown us. Helium turned out to be the second most abundant element in the cosmos, surpassed only by hydrogen. On Earth, it is rare, a light gas that slips from our grip and leaks into space. On the scale of galaxies, it is everywhere, woven into stars and clouds. That abundance is not an accident. It is precisely what the theory of Big Bang nucleosynthesis predicts if the early universe had the proton-neutron ratio and conditions we have been tracing. In other words, when you look at the sun and count how much hydrogen and helium it contains, you are indirectly checking the outcome of nuclear reactions that happened when the universe was only minutes old. The eclipse in India, with its odd yellow line, was one of the first hints that the cosmic recipe really does start with a particular mix. Mostly hydrogen, a substantial amount of helium, and almost nothing heavier at the beginning. You could still, at that stage, dismiss this as a local coincidence. Perhaps our sun happens to have that mix, but elsewhere things are different. To test whether the early universe really stamped the same pattern everywhere, you need to look farther out and further back in time. Light takes time to travel. When you look at the moon, you see it as it was a little over a second ago. When you look at the sun, you see it as it was several minutes ago. Point a telescope at a distant galaxy, and you are looking millions or billions of years into the past, because that is how long the light has been in flight. The universe is not just a place, it is a time machine built into the speed of light. Astronomers use this fact ruthlessly. If you want to know whether the primordial mix of elements was the same in the early universe as it is here, you look for places where matter has not been heavily processed by generations of stars. Most of the gas near us has been through at least one cycle of stellar birth and death. Stars fuse hydrogen into helium and heavier elements, then explode or shed their outer layers, enriching the surrounding space. Over time, the interstellar medium becomes polluted with carbon, oxygen, iron, and beyond. What you want instead are clouds of gas that have hardly been touched, reservoirs of material that still look like the universe did not long after the Big Bang. In the early years of the 21st century, teams using large ground-based telescopes, like those on Mauna Kea in Hawaii, began to find exactly that. They searched the skies for distant quasars, the bright, active cores of young galaxies powered by supermassive black holes. Quasars are useful not only as objects of study in themselves, but as backlights. Their intense light passes through intervening gas clouds on the way to us. Each cloud imprints its own set of absorption lines on the spectrum, telling us what it is made of. Among these, astronomers identified extremely distant, extremely clean clouds, pockets of gas so far away that their light has taken on the order of 11.5 billion years to reach us. In terms of cosmic history, that means we see them as they were when the universe was only a few billion years old, still young compared to its present age. When they analyzed the spectra of these clouds, they found a striking pattern. The gas was almost pure hydrogen and helium, with only trace amounts of heavier elements, far less than in typical gas near our own galaxy today. These are called metal poor or even primordial clouds, and they behave like time capsules. They preserve, in their composition, the outcome of Big Bang nucleosynthesis before stellar activity had much chance to rewrite the ledger. The measured ratio of hydrogen to helium in these distant clouds matches. Within observational uncertainties, the ratio predicted by calculations that start from the physics of the first minutes. The same proton-neutron mass difference, the same freeze-out of weak interactions, the same nuclear reaction rates. You can think of this as a kind of triangulation. On one side, you have theory, a chain of equations describing how an expanding cooling plasma of protons and neutrons should assemble into light nuclei. On another side, you have local observations. The sun's composition, the helium content of nearby stars and gas, and laboratory experiments that pin down nuclear reaction rates. On the third side, you have these distant, pristine clouds, seen when the cosmos was much younger. When all three corners match, something quiet but important has happened. A story that begins with an almost invisible mass difference between protons and neutrons and passes through a brief window of nuclear reactions in the early universe ends up predicting the element mix in places billions of light years away and billions of years ago. If our understanding of the first minutes were badly wrong, the numbers would not line up. The helium fraction in distant gas would be too high or too low. The hydrogen content would be off. But what we see instead is a universe that behaves as though its basic recipe was set early, uniformly, and with remarkable consistency. Of course, none of this happens in isolation. The same observations that reveal primordial element abundances also feed into our measurements of cosmic expansion and structure formation. When you combine them with the faint afterglow of the Big Bang, the cosmic microwave background radiation, and with maps of galaxies in 3 dimensions, a coherent picture emerges. It is not a picture of a universe loosely improvised as it goes along. It is a picture of a universe whose large-scale properties can be traced back to simple, specific conditions in its first moments. The density of ordinary matter, the density of dark matter, the density of dark energy, the spectrum of initial fluctuations, the primordial hydrogen and helium fractions, all can be inferred, in overlapping ways, from independent lines of evidence. This might sound reassuring, as if the more the data agree, the more comfortable we should feel. But in the context of fine-tuning and anthropic thinking, the agreement has a different flavor. It says, the seemingly arbitrary numbers and early events we have been talking about are not just mathematical ghosts. They leave fingerprints everywhere, from the spectrum of a 19th century eclipse to the absorption lines of ancient gas clouds halfway across the observable universe. The proton-neutron mass difference is not only a parameter in a Lagrangian. It is a quiet presence in the yellow line of helium, in the fraction of the sun's mass that is hydrogen, in the very existence of stable stars. The specifics of the early expansion and cooling are not only a graph in a cosmology lecture, they are encoded in the relative heights of the peaks, in the cosmic microwave background, in the pattern of galaxies, in the scarcity of heavy elements in those pristine clouds. In other words, the fine details of the first minutes are not safely quarantined in theory. They are written into the light that reaches a telescope mirror tonight. You can, if you wish, still tell yourself a simple story. The universe is the way it is because it was meant to be this way. Or, it is the way it is because it could not have been otherwise. The data alone do not forbid those narratives. But as the evidence accumulates, what becomes harder to maintain is any belief that the conditions for our existence are vague or easily adjusted. The cosmos we observe is not just broadly suitable for stars and planets. It is tuned, in detail, by very specific numbers and processes whose fingerprints we can trace from laboratory experiments to the edges of the visible universe. Standing under a dark sky, that fact is not obvious. You see points of light, a wash of faint glow, perhaps the pale streak of the Milky Way. If you are lucky, it looks almost simple, but hidden in those photons are the records of element ratios, expansion histories, and early phase transitions. When astronomers speak in quiet, matter-of-fact tones about an eclipse in the 1800s or a gas cloud more than 10 billion light-years away, they are not just collecting trivia. They are testing whether the razor-thin conditions that allow stars, chemistry, and observers really did hold everywhere. For all that time, so far, the universe has answered yes. If the early universe answered yes to the question of whether its numbers would allow stars, the next question is quieter but more personal. Once those stars exist, what exactly do they do to the raw, simple matter they inherit? And how far does their work reach into your own life? The Big Bang does not give you a rich world. It gives you almost pure hydrogen, a substantial dose of helium, and only a whisper of anything heavier. It is a universe with a very short ingredient list. Left that way, it would be a place of pale, structureless clouds, lit perhaps by brief, primitive stars, but empty of rocks, water, carbon chains, and cities. The transformation from that sparse beginning to the cluttered diversity around you happens in stages, and most of those stages take place inside stars. If you think of the early universe as a kind of cosmological kitchen, then stars are the slow, relentless cooks, turning one bland recipe into many. It starts with gravity. Over long stretches of time, slight overdensities in the primordial gas, those little ripples left by early fluctuations begin to collapse. Hydrogen and helium fall inward toward their own collective center of mass, speeding up as they go. The cloud compresses, heats, and spins. At first, nothing particularly dramatic happens. The cloud merely warms under the pressure of its own weight. But as it contracts, the temperature and density in the core rise. Eventually, they reach a point where hydrogen nuclei are pressed together strongly and often enough for the weak and strong interactions to start rearranging them. Nuclear fusion ignites. In the simplest picture, 4 hydrogen nuclei, each a single proton, are gradually combined through a chain of reactions into a helium nucleus with 2 protons and 2 neutrons, plus a release of energy carried away by photons and neutrinos. Different stars follow slightly different paths. Some use the proton-proton chain. Some rely more heavily on cycles involving carbon, nitrogen, and oxygen as catalysts. But the basic outcome is the same. Hydrogen is burned into helium, and light is produced. This process is what holds a star up. Gravity is always trying to pull the star inward, compressing it further. Fusion pushes back, in the form of outward pressure from hot gas and radiation. As long as the fusion in the core can keep supplying energy, the star stays in a kind of dynamic balance. For stars like the Sun, that balance can last for billions of years. A long, calm plateau in which planets can orbit and environments can stabilize enough for complex chemistry to explore possibilities. But fusion does more than hold stars open. It changes the composition of the universe. Every time a hydrogen nucleus is fused into helium, the overall fraction of helium in the cosmos increases and the fraction of hydrogen shrinks. Stars spend the longest stretch of their lives in this phase, quietly converting the most abundant fuel into a slightly heavier ash. When the hydrogen in the core is significantly depleted, the star's internal structure begins to change. The balance between gravity and pressure shifts. In many stars, the core contracts and heats up further while the outer layers expand. The star can swell into a red giant, its envelope bloated and relatively cool, even as its center grows denser and hotter than before. Under those new conditions, helium, once the ash, becomes the fuel. Through the so-called triple alpha process, 3 helium nuclei collide and, in a series of steps, form carbon. Under slightly different conditions, helium can fuse with carbon to make oxygen. This is the moment when elements central to life as you know it first appear in significant quantities. Carbon, with its ability to form long, flexible chains and rings. Oxygen, with its role in water and in energy metabolism. They are not primordial. They are the offspring of tired stars. In more massive stars, the story continues further. After helium burning, if the core becomes hot and dense enough, carbon can fuse into neon, sodium, and magnesium. Later still, those can lead to silicon, sulfur, and elements up to iron. The details are intricate, a nested sequence of burning stages and convective mixing. But the broad picture is clear. The heavier the star and the more massive its core, the more it can climb the ladder of the periodic table before it dies. There is a limit, though. Fusion reactions that build elements lighter than iron release energy. They are downhill in the sense that the resulting nuclei are more tightly bound. Building elements heavier than iron requires energy input. Stars cannot sustain themselves on such reactions. When an iron core grows too large in a massive star, fusion stops being a source of support. Gravity wins. What happens next depends on mass and structure, but one common outcome is a core collapse supernova. The inner core implodes under its own weight. Protons and electrons are crushed into neutrons, and an enormous blast wave tears through the outer layers. In the violence of that explosion, for a brief moment, conditions are extreme enough for rapid neutron capture processes to occur. Nuclei are bombarded with neutrons and pushed far up the periodic table into the realm of gold, platinum, uranium, and many other heavy elements. Some heavy elements are also forged in other catastrophic events, such as the merger of neutron stars. When 2 compact remnants spiral into each other and collide, the torrent of neutrons and the violent ejection of matter produce an environment ripe for assembling heavy nuclei. The light from such events carries spectral signatures of newly minted elements, a kind of flash photograph of cosmic alchemy in progress. None of this material stays locked forever in the stars that made it. Stellar winds, planetary nebulae, and supernova explosions all return processed matter to space. The interstellar medium becomes enriched over time. Where there was once only hydrogen and helium, there are now traces then growing amounts of carbon, oxygen, silicon, iron, and more. With each cycle of star birth and death, the chemical richness of a galaxy increases. Astronomers call the abundance of elements heavier than helium the metallicity of a region. Near the centers of galaxies, where star formation has been intense and many generations have lived and died, metallicity tends to be higher. In the outer, quieter reaches, it is lower. That gradient is more than an abstract statistic. Rocky planets, like Earth, are made largely of metals. In the astronomical sense, silicon, iron, magnesium, oxygen bound into minerals. You cannot build such worlds in a universe that has only hydrogen and helium. You need at least 1 or 2 rounds of stellar processing to seed the gas with enough heavy elements that, when new planetary systems form, there is solid material available to coalesce into terrestrial planets. That means your own existence as a creature on a rocky world already requires a significant history of stellar evolution behind you. The atoms in your bones and blood have likely passed through at least one star, perhaps several. Some were synthesized in long-lived, relatively gentle stars. Some may have been born in the shock front of an explosion or in the debris of a neutron star collision. When Carl Sagan said that we are made of star stuff, he was not being poetic for its own sake. He was giving a literal description of the origin of the elements in your body. The carbon in your cells, the iron in your hemoglobin, the calcium in your teeth, all were assembled first in stellar furnaces and then scattered, only to be swept up again into new structures. This view strips away a particular kind of comforting story. It is tempting to imagine that the universe comes preloaded with everything needed for life, as if the Big Bang were a kind of instant, complete creation. The reality is more like a slow, precarious experiment. The early universe provides a minimal set of ingredients. Gravity and nuclear physics allow those ingredients to collect and cook. Only after long stretches of time and many cycles of stellar death do the conditions for planets and biochemistry emerge. From the standpoint of fine-tuning, stars occupy an ambiguous role. On one hand, they are the engine that takes a simple universe and makes complex chemistry possible. On the other hand, their very existence depends on the same delicate balance of constants we have been circling. If gravity were much weaker, gas might never collapse into dense, hot cores. If it were much stronger, stars might form too quickly and burn too violently to leave room for habitable environments. If nuclear reaction rates or binding energies were different, fusion chains might stall at helium, or skip past carbon, or fail to release usable energy. When you walk through a city at night and see lights in apartment windows, traffic signals changing, the glow of screens, you are seeing the distant, diffused legacy of these ancient, precise processes. The electricity that runs those systems is generated by chemical and nuclear reactions that ultimately depend on the periodic table. The metals in the buildings and the glass in the windows were drawn from ores that formed in an enriched planetary crust. The oxygen you breathe and the carbon dioxide you exhale participate in cycles that hinge on the availability of certain elements in certain ratios. Cities can feel like purely human constructs, divorced from anything as remote as stellar nucleosynthesis. But if you follow the chain of dependencies, the connection is direct. No stars, no heavy elements, no rocky planets with long-term stable surfaces, no complex ecosystems, no such ecosystems, no cultures capable of stacking stone, metal, and glass into dense, luminous structures. From this angle, calling stars alchemists is slightly unfair to most alchemists. Human alchemy never managed to turn base metals into gold. Stellar alchemy did, and much more. It took a universe that began almost entirely as hydrogen and helium, and, through a series of patient, violent, and precisely balanced processes, produced all the texture that later minds would move through and name. Whether you see that as evidence of design, of blind but fortunate physics, or of something stranger, depends on what stories you are willing to entertain. What the science itself insists on is simply this: the path from primordial gas to the periodic table to cities is narrow, contingent, and written in the language of stars. If the path from primordial gas to cities is narrow even inside this universe, it is natural to wonder how narrow the path is across all the universes that never make it that far. Somewhere behind the familiar sky lurks a harsher possibility, that most realities never get past their own beginning. When people first hear about fine-tuning, they often imagine a single universe with a few dials set just right, and then ask whether someone might have turned those dials deliberately. But there is another way to frame it. Instead of starting with one universe that works and asking why, Imagine an abstract space of possible universes, each one defined by a different set of values for the basic constants, a different recipe of initial conditions, perhaps even a different number of dimensions or different kinds of particles. In that space, the cosmos you inhabit is just one point. Move away from it, and you change the strength of gravity, or the mass of the electron, or the amplitude of the primordial fluctuations that seed structure. Shift another step, and you alter the ratio of dark energy to matter, or the binding energy of nuclei, or the charge of the proton. Keep walking, and soon you are in worlds that feel nothing like the one you know. Physicists cannot survey this landscape in any exhaustive way. We do not have a catalogue of all consistent laws of nature. What we can do is play a more modest game. Ask how sensitive familiar phenomena are to small changes in a few parameters. Within that limited experiment, a pattern emerges. The things that make complex life possible, long-lived stars, stable atoms, rich chemistry, planets with persistent surfaces, seem to occupy a very narrow corridor in the larger space of possibilities. Start with gravity. In our universe, the gravitational attraction between two masses is astonishingly weak compared to, say, the electromagnetic force between two charges. At the scale of atoms and molecules, gravity is essentially irrelevant. At the scale of stars and galaxies, it dominates because it always attracts and because masses collect. That separation of scales is crucial. It allows atoms to be light enough that quantum mechanics and chemistry can play, while still letting large clouds of gas collapse under their own weight to ignite stars. If you imagine a universe where gravity is substantially weaker, the balance shifts. Primordial density fluctuations, those tiny ripples left by the early universe, may never grow enough to form bound structures before expansion thins everything out. Gas drifts, but never clumps into galaxies, let alone stars and planets. Space stays a cold, dilute mist. If you imagine gravity much stronger, the opposite problem arises. Clouds collapse very quickly, forming extremely dense objects. Stars, if they form at all, may be massive and short-lived, burning through their fuel rapidly and ending in collapse or explosion. The habitable environments around such stars could be rare, brief, or violently unstable. In some ranges, matter might skip the star phase altogether and tumble straight into black holes. The corridor where gravity is strong enough to gather matter but not so strong that everything falls in on itself in a rush looks, in these thought experiments, remarkably thin. Now adjust the parameters that control the strong and electromagnetic interactions, the ones that set the structure of nuclei and atoms. If the strong force is weaker, many nuclei become unbound. Even the deuteron, the simplest nucleus after hydrogen, might not hold together. Without stable deuterium, the chain of reactions that produces helium in the early universe and powers stars would stall. Without stable helium and other light nuclei, the path to heavier elements closes. If the strong force is stronger, nuclear binding energies change. Some reactions that currently release energy might no longer do so. Stars might burn differently, or not at all in the familiar way. There are ranges in which almost all protons and neutrons would be locked into very tightly bound nuclei, leaving little hydrogen to serve as fuel or as a chemical partner. Tweak electromagnetism instead. Make it much weaker, and electrons would be only loosely attached to nuclei. Atoms would be enormous, fragile, easily ionized. Complex molecules might not survive in the presence of even modest radiation. Make electromagnetism much stronger, and electrons would hug nuclei too tightly. Atomic sizes shrink, and the transitions between energy levels become more extreme. The subtle sharing of electrons that allows carbon to form long chains and rings, the backbone of organic chemistry, could be disrupted. The mass of the electron is another narrow constraint. If it was substantially larger, atomic orbitals would change, altering the entire chemistry of the periodic table. Certain bonds would be impossible or prohibitively energetic. A very light electron, by contrast, would give very diffuse atoms with their own instabilities. Life, as far as we understand it, depends on a peculiar sweet spot where atomic sizes, bond energies, and thermal energies all live in comparable, but not identical, ranges. Add in dark energy, the term we use for whatever is driving the accelerated expansion of the universe. In our cosmos, its effect is mild in the early era when galaxies are forming. It becomes dominant only later, when large-scale structure is already in place. If the dark energy density were much higher, the expansion would start accelerating strongly much earlier. Matter would be whisked apart before it could collapse into galaxies and stars. You would get a universe in which the average separation between atoms grows rapidly, but almost nothing ever congeals into something as dense as a star, let alone a planet. These are not wild speculations about aliens or alternate histories. They are simple, conservative extrapolations from the physics we already use, asking, what if this number were doubled, or halved, or shifted by some modest factor? In many cases, the answer is not, life would be slightly harder, but the basic building blocks of complexity would never appear. The phrase narrow corridor is one way to visualize this. Picture a high-dimensional space, each axis representing one parameter: the strength of gravity, the mass of the electron, the value of the cosmological constant, the ratios of quark masses, and so on. Most points in this space correspond, as far as we can tell, to universes where either nothing much happens or where things happen so violently that no stable, intricate structures survive. Some regions give you universes filled with short-lived, massive objects that flare and die. Some give you near emptiness. Some give you an ocean of black holes. Some give you only diffuse gas with no stars. In others, chemistry is crippled. No stable hydrogen, no carbon, no water, no periodic table beyond a sprinkle of nuclei that cannot combine into interesting forms. Threading through this space is a thin, twisting corridor where the values are just right to permit long-lived stars, robust chemistry, and a decent supply of heavy elements. Your universe, or at least the part you can see and measure, appears to sit somewhere in that corridor. Computer simulations of cosmic structure underscore this picture. When cosmologists run numerical experiments in which they nudge parameters away from their measured values, they often see the web of galaxies and clusters either fail to form or morph into something radically less hospitable. For certain changes, the universe still organizes itself, but into patterns with no obvious niches for complex life. For others, the result is a fleeting flash of structure that collapses or disperses before anything stable can arise. From the human side, it is tempting to take this narrowness as a compliment, as if the universe had undergone a demanding selection process whose sole purpose was to make a world that could host you. But the same data can be read in a colder way. If there is any mechanism, known or unknown, that produces many universes with varying parameters, then almost all of them will never contain observers. They will die in the egg, either as near featureless expansions or as quick, violent bursts of physics that never slow down enough to form something like a brain. In that picture, there is nothing especially flattering about finding yourself in one of the few universes where the corridor is wide enough to walk down. It is simply inevitable that any being capable of asking the question will be standing in such a place. No one wakes up on a planet made entirely of lava and wonders why the atmosphere is breathable. You, by definition, wake up only in rooms where there is air to breathe. The narrow corridor is unsettling precisely because it denies you a comfortable middle ground. Either the constants and initial conditions in your universe are deeply necessary, in some way you do not yet understand, or they are one random draw from a vast space in which almost every other draw leads to silence. In the first case, you live in a cosmos that had to be life-friendly for reasons that go beyond you. In the second, you live in a statistical fluke that feels inevitable from the inside, but is, from the outside, just one non-zero entry in a sea of zeros. Neither option gives you the simple story we like to tell ourselves, that the universe is big, indifferent, and basically okay for life in most places. The evidence, as far as we can currently read it, points instead toward a reality in which most imaginable universes never get around to making stars, let alone questions. If most possible universes never get to ask anything at all, then the fact that you are here, thinking about them, is not just comforting. It is suspicious. It means your very act of wondering is already evidence that you are not seeing reality from a neutral seat. For most of its history, science has tried to do the opposite. It has trained itself to step away from special places and special times. The Copernican instinct is to scrape off every assumption that says, "We are at the center," and replace it with, "We are probably ordinary." My 3. On PSIs. But in the middle of the last century, some physicists began to realize that there is another kind of specialness that you cannot easily scrape away. The fact that you exist at all. Not as a species, not as a culture, just as any kind of conscious observer. Robert Dicke, an American physicist working in the 1960s, was one of the first to push this idea clearly. He noticed something about cosmic timing, the age of the universe, the age of the sun, the conditions on Earth. They are not random along the cosmic timeline. They line up in a way that is oddly convenient for beings like us. The early universe, right after the Big Bang, had almost no heavy elements. It was a simple mixture of hydrogen and helium, with only traces of anything else. Carbon, oxygen, iron, and all the other ingredients of planets and bodies had to be cooked later, inside stars, and then scattered. Stars must live, fuse, and die before their products can be reused. At the other extreme, if you wait too long, stars like the sun exhaust their fuel and die. The universe goes dark and dilute. The heavy elements are still there, but the steady, long-lived energy sources that might support complex life are gone or rare. Dicke's point was quiet but sharp. Conscious observers cannot show up just anywhere in this long drama. There is a window of time when enough heavy elements have been made to build planets and bodies, but the stars that sustain life have not yet all burned out. You and I find ourselves inside that window not because it is special in some cosmic moral sense, but because outside it, there is no one to find themselves anywhere. This way of thinking is what later came to be called anthropic reasoning, not anthropocentric, which would put humans back in the center as the purpose of everything, but anthropic, which simply means related to observers like us. It is an attempt to build into our reasoning the obvious but easily forgotten fact that any description of the universe made by observers must be conditional on the existence of observers. In 1973, at a conference in Krakow marking the 500th anniversary of Copernicus's birth, the physicist Brandon Carter proposed a clearer formulation. He suggested that the Copernican Principle, the idea that we do not occupy a special place in space, had to be balanced by an anthropic principle, that our observations are not made from a randomly selected point in all of space and time, but from a point that already satisfies the conditions needed for life. There are many versions and arguments and subcategories, but the gentle core of the anthropic principle can be stated almost in plain language. You should not be surprised to find that the universe looks compatible with your existence, because if it did not, you would not be here to be surprised. On the surface, that can sound like a tautology, something empty, dressed up as insight. But consider how it actually changes the way you interpret certain coincidences. Suppose you wake up in a hotel room and notice that the building is not on fire. The oxygen level is comfortable, the temperature is stable, the walls are not collapsing. You could be amazed at your good fortune, or you could recognize a basic filter. You cannot wake up alive in a burning, collapsing room and calmly reflect on your situation, because the conditions that permit calm reflection are already restrictive. Your very state of being awake and aware selects a subset of all possible hotel states. The anthropic principle applies the same logic to the entire universe. When you look around and see a cosmos whose constants seem narrowly tuned to allow stable matter, long-lived stars, and complex chemistry, your first instinct might be to say, "How lucky? What are the odds?" But from an anthropic perspective, the better question is, given that I am here as a conscious system, what should I expect my surroundings to look like? If there are many possible universes, or many possible regions of a larger reality with a wide range of physical constants, then most of those regions will be sterile. Nothing that asks questions will ever form there. In the minority of regions where the constants allow life, observers can emerge and later look around. Naturally, they will see a world whose rules, in retrospect, look remarkably well suited to them. In that frame, the apparent fine-tuning is not surprising. It is not a bonus feature added on top of a random draw. It is a precondition for anyone to be present. Just as every lottery winner feels uniquely lucky, even though it was guaranteed that someone would win, every observer in a life-friendly universe feels as though their universe must be special. This does not require any mystical assumption about destiny. It is a selection effect. You are sampling reality from within the subset of places where sampling is possible. That bias is not optional. It is baked into every observation you make. There is a tension here with the Copernican instinct, and it is worth feeling rather than smoothing over. On one hand, we have learned not to place ourselves at the spatial center of anything. The universe, on large scales, looks roughly the same in all directions. Our galaxy is not in a privileged position. Our star is ordinary. Our planet is small. On the other hand, in the space of possible universes, we seem to be in a very special region. The narrow corridor where constants and conditions allow observers. The Anthropic Principle says that is exactly where you should expect to find yourself and nowhere else. The Copernican Principle says you should not mistake that necessity for cosmic favoritism. Anthropic reasoning is slippery because it can easily be abused. It is tempting to use it as a universal solvent. Whenever you see an awkward coincidence in physics, you say, well, if it were different, we would not be here, and stop thinking. That is not its honest use. Used carefully, it is a constraint, not a conclusion. It tells you that any viable theory of the universe must be compatible with the existence of observers somewhere in its structure, but it does not tell you which theory is true. It also does not, by itself, explain why there should be a multiverse, or a mechanism generating many different universes with different settings. It says, if such a mechanism exists, then our being in a life-friendly pocket is unsurprising. It does not provide the mechanism. There is another subtlety. Anthropic arguments often talk about observers in very abstract terms. They do not require humans or even biological life in the familiar sense. They require only systems complex enough to register information about their environment and to be sensitive to its conditions. In that way, the Anthropic Principle is less about human specialness and more about the minimal requirements for any kind of awareness to arise. Still, when you apply it to our specific universe, it has teeth. Consider the cosmological constant, the energy density of empty space that drives the accelerated expansion of the universe. The value we measure is tiny compared to many natural scales in particle physics, yet non-zero. If it were much larger and positive, expansion would have accelerated earlier and more violently, preventing matter from collapsing into galaxies at all. If it were large and negative, the universe could have recollapsed quickly. Anthropic reasoning says, perhaps there is a range of possible vacuum energies, and we find ourselves in the region where its value is small enough to allow galaxies to form before acceleration tears structures apart. That is not a proof, but it shifts the tone from "what an inexplicable coincidence" to "of course civilizations will only arise where this constant has a value in the narrow life-friendly band." The same goes for the age of the universe you measure, the metallicity of your environment, the mass and luminosity of your star. Each of these quantities could, in principle, take on many values across different regions or histories. You find yourself in a universe of a certain age, with a certain chemical richness, orbiting a star of a certain type. Those facts feel personal, but they might simply be the typical conditions in which observers can exist, not evidence that the universe has shaped itself specifically for you. If this sounds cold, it is worth noticing that it is also honest. The Anthropic Principle does not close the door to meaning, but it refuses to smuggle meaning in through the back door of coincidence. It says, start by acknowledging that you are not a neutral witness. Your existence has already filtered the kinds of universes you can see. You can respond to that in different ways. One reaction is resignation. To say that everything is a selection effect, and therefore nothing has deeper significance. Another is defiance. to insist that the fine-tuning is too sharp to be explained by statistics, and therefore must be evidence of design. A third response, quieter and harder to hold, is simply to accept the conditional nature of your knowledge. To admit that every statement you make about the universe is made from a living seat inside a narrow corridor of possibilities, and that this seat shapes what you can see and how you interpret it. In that sense, the Anthropic Principle is not really about physics at all. It is about epistemology, about what it means to know anything when your existence is not optional data but part of the system you are trying to describe. From this angle, the universe does not look perfect. It looks survivable, barely, in a few small patches, for a short time, under stringent conditions. The fact that it feels perfect to you may say more about you, about the bias of a creature that can only wake up in worlds where waking up is possible, than it does about whatever reality is beyond the slice you are allowed to inhabit. If every observation you make is already filtered by the fact that you are alive to make it, then any explanation of why the universe looks the way it does will also be, in some sense, about you, even when it pretends not to be. Once people absorb the basic anthropic idea, they tend to drift toward one of a few large story families. Each one tries to answer the same quiet question. If the constants and early conditions really sit in a narrow, life-friendly band, why do they sit there at all? Not just why they seem that way from inside, but why there is any such universe to sit inside of. One family of answers says, because someone or something wanted it that way. Another says, because we are inside a constructed environment, a kind of simulation whose parameters were set by designers for their own reasons. A third says, because there are many universes with many settings and we simply live in one of the rare ones where anyone can live. Call them, loosely, design, simulation, and multiverse. They are not precise theories so much as narrative frameworks. You can fill each one with different details, add symbols or equations or metaphors, but the basic shape stays the same. Start with design. In this story, the universe is the way it is because some kind of mind chose the laws and constants. It might be a single creator, or a hierarchy of beings, or something stranger that does not fit human categories well, but the key move is the same. Intention precedes existence. The constants are not accidents, they are settings. The narrow corridor of life, friendly universes, is not a rare coincidence. It is the goal. This view aligns naturally with many religious traditions. For people who already believe in a creator, the idea that the cosmos is finely tuned for life fits comfortably as an expression of care or purpose. The existence of minds is not something that needs to be explained by physics alone, because mind is already present at the beginning of the story, choosing which physics to instantiate. From the standpoint of empirical science, though, design sits in an awkward place. You can always say that a designer chose the constants to be what they are, but it is hard to turn that into testable predictions. If the constants had been different, you could say that a designer had chosen those instead. If the universe were empty and sterile, one could still imagine a creator who for some reason wanted a barren work. In other words, design is flexible. It can accommodate almost any observational outcome. That makes it resilient as a worldview, but it also means it does not, by itself, give science much to grab onto. Physics can study the structure and behavior of the universe given its laws. It cannot easily reach outside those laws to interrogate motives, especially motives that might belong to something beyond space and time as we understand them. There is also a subtler point. Even in a designed universe, anthropic selection would still operate. If a creator made many possible worlds with different properties, observers would still find themselves only in those that support observers. Design does not remove the selection effect. It only moves the question back a step. From why this universe, to why did the designer want life at all, and why this particular form of life? At that stage, you are doing philosophy or theology, not physics. The second family of stories keeps the idea of deliberate choice, but relocates it inside a larger physical framework. This is the simulation picture. In the early 2000s, the philosopher Nick Bostrom framed a simple argument. Roughly, he said, imagine that technological civilizations continue to advance. Eventually, they might have enough computing power to run detailed simulations of their own ancestors or of entire universes. If they choose to do this on a large scale, there could be enormous numbers of simulated worlds for each base-level world. If conscious experience can arise in such simulations, then most observers with experiences like ours would actually be simulated. If you take that seriously, and if you do not think it is impossible to simulate conscious beings, you are led to a strange trilemma. Either almost all civilizations die out before they can run such simulations, or they survive but choose not to run them in large numbers, or they do run them, and therefore almost any observer who wonders about their place in the cosmos is probably inside one. In the simulation story, fine-tuning can be recast as design, but at a different level. The parameters of our universe are what they are because some simulator, somewhere up the chain, set them that way. Perhaps they chose life-friendly settings because they wanted to study the emergence of civilizations. Perhaps they chose values that maximize the complexity or aesthetic interest of the resulting structures. Perhaps we are, from their point of view, just one run among many. Popular culture has seized on this idea in many forms. Films like The Matrix use it as a metaphor for alienation and control. The world you experience is a virtual construct, and the true reality is hidden. That image is compelling because it mirrors a feeling many people already have, even without any cosmology attached, the sense that everyday life might be a surface over something more fundamental. From a physics perspective, the simulation proposal raises sharp questions about testability. If the simulation is good enough, then the inhabitants cannot easily distinguish it from a base-level reality. The constants they measure, the particles they detect, the cosmic background radiation they map, all would be part of the software. Any apparent limitations, such as a maximum speed of information transfer or a quantum graininess to space, could be either fundamental features of the simulated laws or artifacts of the underlying hardware. People sometimes suggest looking for glitches, for evidence of discretization in energy levels beyond what known physics predicts, for anomalies in randomness. But an advanced simulator could, in principle, hide such traces or fold them into the apparent laws. The more powerful the hypothetical simulators, the harder it becomes to imagine any definitive experimental disproof. At that point, the simulation story starts to look similar to design in one crucial respect. It can explain fine-tuning by appealing to choices made by unseen agents, but it struggles to offer unique, falsifiable predictions that distinguish it from non-simulation realities. It may be logically coherent and even probabilistically suggestive in some frameworks, but it sits at the edge of what science, as a method, is built to handle. The third family of stories replaces intention with multiplicity. This is the multiverse picture. Here, the apparent fine-tuning of our universe is explained not by a designer or a simulator, but by a large ensemble of universes, each with different parameters. The idea takes different forms in different theoretical contexts. In some versions of inflationary cosmology, the rapid expansion of space does not end everywhere at once. Instead, it ends locally, forming bubble universes that keep budding off from an eternally inflating background. Each bubble could, in principle, have different values of the constants, set by how symmetries break as it cools. In some versions of string theory, there is a vast landscape of possible vacuum states, each with its own pattern of compactified dimensions and its own low-energy physics. Different regions of a larger meta-universe could settle into different vacua, realizing different effective laws. In both cases, and in other variants, the core idea is the same. The space of possible laws and constants is not merely abstract, it is populated. There are many universes, with many settings. We live in one where the settings happen to allow stars, chemistry, and observers. The Anthropic Principle then becomes a statistical filter. Of course, we see life-friendly values. There is no one in the life-hostile regions to be puzzled by their hostility. The multiverse story has a certain scientific appeal because it can, in principle, be connected to specific mathematical frameworks. Eternal inflation and string landscapes are not just metaphors. They arise from attempts to extend known physics. But there are serious difficulties. The first is empirical access. If other bubble universes exist beyond our observable horizon, we may never interact with them. Light from them may never reach us. Their particles may never collide with ours. Without any direct observational contact, how can we confirm or disconfirm their existence? Some proposals suggest subtle signatures, such as scars in the cosmic microwave background from bubble collisions, but so far no clear, agreed-upon evidence has appeared. The second is the so-called measure problem. In an infinite multiverse with infinitely many regions, each realizing different values, how do you define probabilities? What does it mean to say that a certain kind of universe is rare or typical when there are infinitely many of each? Different ways of regulating those infinities can give different answers, and there is no consensus on which, if any, reflects physical reality. Because of these issues, the multiverse often feels like a halfway house between physics and philosophy. It emerges from serious attempts to understand high-energy theory and cosmology. Yet it also extends beyond what current experiments can probe. For some, it is an elegant way to tame fine-tuning without invoking intention. For others, it is an extravagant multiplication of entities with no clear payoff. If you step back, all three story families, design, simulation, multiverse, can be seen less as competing scientific theories and more as different ways of metabolizing the same unease. The universe looks strangely hospitable to life, given how narrow the conditions seem to be. The Anthropic Principle explains why we should not be shocked by that from the inside, but it does not answer the deeper, why is there any such universe question. Design answers by saying, because some mind chose it. Simulation answers by saying, because some mind constructed it as a model. Multiverse answers by saying, because reality is large enough that even extremely rare configurations must occur somewhere, and we are in one of those. Notice what is common to all of them. None can currently be confirmed or ruled out by the data we have. None changes the detailed workings of the physics you can test in the laboratory or observe with telescopes. All of them, in different ways, stretch beyond the domain where equations and experiments can give clean verdicts. That does not mean they are worthless. Humans think in stories. When faced with an apparent pattern that feels too sharp to be comfortable, we reach for narratives that can hold both the pattern and our discomfort. These mega-stories tell you less about what the universe is and more about what kinds of answers you are willing to live with. If you are drawn to meaning and purpose, design may feel natural. If you are drawn to hierarchy and hidden machinery, simulation may resonate. If you are drawn to impersonal statistics and vast structures, multiverse thinking may seem honest. Each choice reveals something about your preferences, your fears, your appetite for randomness or intention. The universe itself, meanwhile, remains quiet. It presents you with a specific set of constants, a specific history of expansion and structure formation, a sky full of stars whose light carries the imprint of early conditions. It does not label itself as designed or simulated or one bubble among many. Those labels are ours. Standing under that sky, you can pick any of these grand narratives, or none. You can treat the fine-tuning problem as a clue, or as a mirage, produced by selection effects, or as both at once. What you cannot honestly do, at least not with the tools of physics alone, is claim certainty. The data underdetermine the story. That lack of closure is not a flaw in the universe. It is a boundary in our understanding. Whichever of the great stories you lean toward, none of them change a simpler, harder fact. Whatever this universe is, it is not particularly kind to the things that live inside it. From close up, existence feels improbably tailored. From far away, it looks more like a brief exception scratched into something overwhelmingly hostile. Start at the largest scale. Most of the cosmos is not warm and bright and breathable. It is near vacuum, a darkness between stars, where a handful of atoms drift in volumes larger than anything you can meaningfully imagine. Temperatures hover just above absolute zero. Radiation from ancient explosions and distant galaxies slips silently through, carrying energy that, more often than not, will never be absorbed by anything living The places where matter actually clumps into stars and planets do not automatically become hospitable. Around many stars, the space where liquid water could exist on a rocky surface is a thin shell, a narrow band of distances. Too close, and any atmosphere may boil away. Too far, and everything freezes. Outside that band, worlds can still exist, but they are not the kind that allow people to stand barefoot under a sky and breathe without machinery. Even among the stars themselves, most are not sun-like. Many are smaller and cooler, prone to violent flares that can strip atmospheres from nearby planets. Others are massive and short-lived, roaring through their fuel and ending in explosions long before complex chemistry has a chance to assemble bodies and minds on orbiting rocks. There are also the things that do not shine in a friendly way at all. Black holes. Regions where gravity is so strong that not even light can escape. Sit at the centers of galaxies and in the wreckage of dead stars. Their presence shapes the orbits of stars, the flows of gas, the growth of structure, but they offer nothing like a habitable surface. Gamma-ray bursts brief. Intense flashes of high-energy radiation can sterilize regions of space if they strike with sufficient strength and proximity. From a distance, the universe looks less like a designed living room and more like a hazardous industrial site, in which a few corners happen, accidentally, to be just cool and quiet enough for something delicate to take root. Even your own planet, which may feel like a natural home, carries the same ambivalence. Earth has an atmosphere thick enough to shield you from much of the sun's ultraviolet radiation and from smaller meteoroids, yet thin enough that you can move and breathe. It has liquid water on its surface and a temperature range that allows fragile organic molecules to remain stable. Its magnetic field deflects many charged particles. Its orbit is nearly circular. Its axial tilt gives you seasons without swinging into extremes. Taken together, these features are easy to romanticize. They invite the language of balance and harmony. But if you read the geological and biological record, what emerges is not a steady, gentle nurturing so much as a series of narrow escapes. The history of life on Earth is marked by repeated mass extinctions. There have been times when volcanic eruptions flooded continents with lava and choked the air with ash and greenhouse gases. Times when oceans turned anoxic, suffocating many marine species. Times when climate shifted abruptly, locking the planet into ice or pushing it into heat. One of the most famous episodes came roughly 66 million years ago, when a large asteroid or comet struck what is now the Yucatan Peninsula. The impact hurled dust and vapor into the atmosphere, triggering wildfires and blocking sunlight. Food chains collapsed. The non-avian dinosaurs, which had dominated the land for tens of millions of years, disappeared. Many other species vanished with them. From the standpoint of a small mammal sheltering in the aftermath, that disaster was an opening, an opportunity for different lineages to expand and diversify, eventually giving rise to primates and, much later, to you. From the standpoint of the dinosaurs, it was simply annihilation. The same event can look like creative fine-tuning or brutal indifference, depending entirely on where you sit in the story. Even in quieter periods, the biosphere is not a stable paradise. Species appear, last for a while, and vanish. Most of the organisms that have ever lived are gone. The line that leads to humans is one of many branches, most of which ended without leaving descendants you would recognize. Evolution is not a gentle hand guiding life toward consciousness. It is a relentless blind filter that preserves whatever happens to work well enough under current conditions, until those conditions change. When Douglas Adams described Earth as an insignificant little blue-green planet orbiting an unremarkable star in the unfashionable end of a spiral arm, the joke landed because it undercut our tendency to see our home as central and blessed. But there is a darker corollary. If someone did in fact design the universe for us, they chose to house us in a place that regularly attempts to kill us. This contrast points to an important distinction that often gets blurred. A universe can be fine-tuned to allow life without being fine-tuned to pamper life. The first requires only that there exist some pockets where the conditions for complex chemistry and stable energy sources overlap for a while. The second would require that those pockets be common, durable, and gentle. What we see looks much more like the first. Think of a flower growing from a crack in a cliff face. The rock is not built for the flower. It is indifferent stone. The conditions at most points along its surface are too dry, too exposed, too inhospitable for anything delicate to survive. But in one small crevice, enough soil and moisture collect. A seed happens to land there, and for a season, a plant exists. If the flower could think, it might look up at the cliff and the sky and feel that it lives in a perfect world. The sunlight is at just the right strength. The wind usually is not strong enough to rip it out. Water arrives now and then in a way that, from its perspective, feels almost intentional. But an observer stepping back would see something else, an environment that is overwhelmingly hostile, with a small tolerated exception. Our situation may not be so different. The fact that you can breathe at sea level without harm does not mean the universe was designed as a breathable space. It means you evolved in one of the few thin layers of matter where the local chemistry and physics happened to sustain organisms like you. Above that layer, high in the atmosphere and beyond, radiation and cold and vacuum quickly return. Below it, in the depths of rock and mantle and core, pressures and temperatures reach levels that would crush or melt you. This perspective makes another puzzle sharper. For decades, humans have been listening for signals from other civilizations, pointing radio telescopes at the sky, scanning for patterns that would betray artificial origin. So far, the result has been silence. That silence could mean many things. Perhaps intelligent life is extraordinarily rare, and we are among the first. Perhaps it is common but does not use technologies we can detect or does not last long enough to spread widely. Perhaps we have not listened in the right ways or at the right times. Whatever the explanation, the absence of obvious neighbors sits uneasily next to the idea of a universe exquisitely tuned for life. You might expect a genuinely life-friendly cosmos to be visibly teeming, full of biospheres and minds and artifacts. Instead, from where we are, it looks mostly empty. We see chemistry. We see physics. We do not yet see many signs of other stories, like ours. That gap between apparent fine-tuning and apparent loneliness is another crack in the notion of a universe made for us in any comforting sense. It suggests a different picture, a reality where the conditions that allow life are rare and fragile, and where even when they are met, nothing guarantees that life will appear or that it will survive, or that it will do anything in particular with its brief window. You can, of course, respond by tightening the circle. Perhaps the universe is made not just for life, but specifically for human life, on this one planet, in this one era. That belief is difficult to reconcile with the scale and violence of everything beyond our atmosphere, but it is psychologically coherent. It replaces a hostile vastness with a backdrop, or you can lean into the discomfort. You can accept that the same physics that allowed your brain to form also permits supernovae, asteroid impacts, lethal radiation, and eventual heat death. The constants that keep atoms stable and stars burning do not contain a clause exempting delicate structures from the general rule that everything dissolves. Seen this way, the universe is not your enemy and not your friend. It is a set of rules that, in one narrow corridor of possibilities, allows something like you to exist for a while. The brutality and the beauty are two faces of the same underlying patterns. The supernova that sterilizes a region of space is also the event that spreads heavy elements into the interstellar medium, enabling future planets. The unstable climate that threatens modern civilization is the same climate system that, over deep time, has shifted and varied in ways that may have spurred evolutionary innovation. None of this makes the dangers less real. It does, however, erode a particular notion of perfection. If by perfect you mean safe, gentle, tailored to your comfort, then the universe fails badly. If by perfect you mean perfectly arranged to produce and sustain life everywhere, all the time, it fails that test too. And yet, from inside the small pocket where you happen to be alive, it can feel perfect. Because any deviation from the conditions you know would simply mean you were never here to judge it. The universe does not need to be optimized for you to experience it as just right. It only needs to be barely compatible with beings that are wired to treat survival as the baseline, and anything beyond that as a kind of grace. In this light, calling the universe finely tuned is almost a statement about human perception. You are tuned to notice the ways in which the world fits you, because your senses and cognition evolved under those fits. You are much less attuned to the immense regions where nothing similar could exist. They slip out of your emotional frame, even as you know about them intellectually. The result is a kind of illusion of centrality that persists even after you have accepted that Earth is not in the center of space. You still live, unavoidably, at the center of your own survivable bubble. And you still tend to judge the universe from that vantage. When you step back, the picture changes. You see a universe that allows life in a few small, temporary niches and is indifferent everywhere else. You see a cosmos where the same laws that let you think about meaning also guarantee that, given enough time, both you and the structures that support you will come apart. Whether you find that thought crushing or liberating is, again, a reflection not of the universe but of you. Maybe the most unsettling realization in all of this is also the simplest. The universe does not feel perfect because it was made for you. It feels perfect because only in places like this, and only for a time like this, can something like you appear and notice anything at all. Once you see that, a lot of familiar questions twist slightly out of shape. Why is the universe so well suited to life? Becomes, what kind of universe could produce a thing that asks that question? Why do the constants look fine-tuned? Becomes, from which kinds of worlds could anyone complain that they look fine-tuned? At a technical level, nothing changes. The equations remain the same. Protons remain very slightly lighter than neutrons. Stars keep burning hydrogen into helium. Galaxies keep drifting apart under the influence of dark energy. The anthropic lens does not adjust any dials. It only reminds you that your vantage point is already pre-selected by survival. But on the level where you actually live, in choices, in fears, in late-night thoughts under a dim sky, it does shift something. If the universe does not promise meaning, then meaning is not something you can find lying fully formed out there, waiting to be discovered like a new element. It is something that emerges because configurations of matter arose that could care. A rock does not worry about fine-tuning. A star does not ask whether the universe is designed. Molecules do not debate simulations or multiverses. Consciousness is what turns the bare fact of existence into a problem, a question, a story. You can take that as a demotion. In a certain light, it is. Instead of being the point of the universe, you become a side effect of particular constants and initial conditions. Your values, your projects, your relationships are not written into the fabric of space-time. They are contingent, local patterns, like weather. At the same time, there is a strange, quiet dignity in that picture. Out of all the ways reality could have failed to notice itself, you happen to inhabit one of the ways it does not. In one small region, for one small span of cosmic time, matter arranged itself into forms that can feel pain and beauty, can build detectors and telescopes, can argue about philosophy, and write music, and worry about whether anything matters. The universe did not have to be like that. It also did not have to be any other way. It simply is, with these constants and this history. Inside that given backdrop, you are the one who decides what to do with the fact that you got a seat at all. You do not choose the laws of physics, but you choose how you treat other beings who are trapped under those same laws. You do not control the expansion of space, but you control what you do with the few square meters around you. You cannot extend the lifetime of stars, but you can decide what kinds of stories, institutions, and traces your brief civilization leaves behind while the stars are still burning. If someday, far in the future, someone or something were to replay this universe like a film, most of it would look utterly indifferent. Expansion, collapse, fusion, decay. The segments where minds appear would be thin threads in the total running time. The question that remains in your hands is simple and impossible at once. What do you want those thin threads to look like? You are not here because the universe is kind. You are here because, in one narrow corridor of possibility, it allows beings that can ask why to exist for a moment. That moment will end, on individual scales and on cosmic ones. The constants that made you possible will eventually also unmake everything you know. In between, there is this, a finite window in which you can look up, understand a little of how precarious your situation is, and still decide to care about something anyway. Not because the universe guarantees it, but precisely because it does not.